Happy day and welcome everybody. What we're talking about today is solubility. So what is solubility? Solubility is the solubility of something to dissolve into something else, okay? And so now I want to make sure that we understand too that sometimes things can dissolve, but they're not necessarily ionizing. And so I want to make sure that right from the start, we kind of take a look here and get an idea of what is happening. So I've got some salt inside of this bowl, and we're going to drop the salt inside of the bowl. And what you're going to notice is this, yes, is going to dissolve the salt, but it is also going to ionize the salt. And if we can pause this, what we notice is the positively charged sodiums should have negatives, which are these red oxygens. That's what actually pulls those sodiums apart. And the chloride, the negative chloride, should actually have the positive white hydrogen part of the water molecule that has basically pulled that apart. Now, dissolving or solvation is what they call it, is actually a three-step process, and so we're going to get into that in just a little bit. Okay, now let's take a look to see what happens where instead I add the sugar molecules. Well, if you add the sugar molecules, yes, sugar dissolves in water, but it's not ionizing in the water, okay? And so when we talk about the solubility of something, we're typically talking about, does it break up into ions? That's usually where we're going when we talk about how soluble something is, okay? It can reference simply dissolving, but if we're saying that it's going to be like an aqueous solution, we typically will say, is it giving us charges, positive, negative charges, okay? So just to kind of keep that in mind before we get started here with the notes, okay? So let's take a look here, and we are talking solubility, all right? What is this solubility? So it says it's the amount of substance that dissolves in a given volume of a solvent at a given temperature. Now, the solubility of a solid in any solvent always can change. As soon as you change your temperature, you can actually change how soluble it is. Okay, so almost always, if you change the temp, you'll change the solubility. It's determined by both the solute and the solvent, and so the units that we typically give it is we say it's grams of solute, but in this case, it's going to be per liter of solvent. So the way that we say what is solubility, so if you wanted an equation for it, it is grams of the solute. Now, you could even use moles, but typically we'll use grams, and you can convert it back and forth. And again, it's typically per liter of the solvent that you put it in, okay? And so how soluble is it? And so we know that it can dissolve, or if you go backwards and you have a solution and then you evaporate the water off, then it can recrystallize, okay? So there are what are called saturated solutions. And so all a saturated solution is it's a solution in equilibrium, basically holding the maximum amount of solid that it can. So with the max amount of solid having dissolved all of the solid that it can hold at that particular pressure and temperature, okay? Now, if it's an unsaturated solution, then it's simply a solution that contains less. That's pretty easy than when it's saturated. I'm going to show you this in just a second. Then the question is, what is a supersaturated solution? Okay, so let me take you to the simulation here real quick. What I have here is I have some cobalt chloride, and this is just water right now. And so I'm just going to drop some cobalt chloride in. And what we're going to see is, you can see that the color is light first, okay? And as I increase the concentration, so if we look at the concentration number, it's at 0.49 right now, I know that as I increase my concentration, my color is actually getting darker. It's getting to be a deeper and deeper pink, okay? Now, I have not reached the point where my solution has become saturated yet, but I might, okay? And how do I know when I've reached the point where it's saturated? Well, what's going to end up happening is my concentration will stop changing. So I'm at a 3.16 right now. My concentration's at a 3.65. Let's keep on going. It's 4. Oh, there we go, 4.330. Okay, now, here's a misconception, okay? So I can see that there's actually little teeny tiny solid particles that are no longer dissolving inside of the solution. So that's how I know it's saturated. People will think, if I keep adding more, now it's supersaturated. That's incorrect, okay? Supersaturated, even though by definition it says that it's holding more solid than it actually can, that's not how you create a supersaturated solution. So I'm going to show you what a supersaturated solution looks like. This is a supersaturated solution. I have to be really careful with it. A supersaturated solution of sodium acetate, NaC2H3O2-, okay? Now you're thinking, it just looks like water, okay? Now when I made this, I basically added, I believe it was about 50 grams of the sodium acetate, and I only added about 3 milliliters of water to it, okay? And then what I did, and it was pretty much all solid still, okay, is I heated it up. This is how you create a supersaturated solution. So what has happened here, and now I cooled it down, and after I cooled it down, so I got all of these crystals that were all sitting along the bottom, I got these to go into solution by heating it up, by increasing the temperature. And then I cooled it down, and now it's supersaturated. Now, what's going to happen with this is, if I take a couple of crystals, now I'm literally just going to take, so I have a solid container of my sodium acetate here, okay? And what I'm literally doing is just taking, I just put a little bit inside of here. I just barely want any, and you can't actually make sodium acetate by yourself. All you need is vinegar, which is acetic acid, and salt, sodium chloride, and you can actually make your own sodium acetate. Okay, so I've got some crystals right on like the tip of my finger here, and all I'm going to do is I am going to give them one little tiny seeding crystal. And what's happening? Oh my gosh, it's all crystallizing. Okay, so if I feel this, it actually feels warm, okay? And this is super cool. So before it was like a liquid. Oh, let's make sure. Yep, there we go. And so now I can just like flip it upside down, and so you can see it totally crystallized. And so that's a supersaturated solution of sodium acetate, okay? So in order to create a supersaturated solution, it's not just I added a whole bunch more of the solid in there. And this is really warm, by the way. This feels really nice. You actually have to heat it up, and then you get the solid to go into solution, and then you cool it down, and that's what makes it supersaturated. All right. So how do we prepare it? All we really need to do is we need to take a saturated solution prepared by heating a saturated solution, and then you cool it down, and the solute is now less soluble, okay? Now, what determines solubility? There's a term that they use, and it's miscible, M-I-S-C-I-B-L-E. And that just means that you can mix it all up, so it's miscible, okay? And another thing that determines solubility is, are they substances with similar IMFs? And are they like soluble in one another? There's a cardinal rule, but I'm going to tell you the AP will never want you to use this term, okay? So if you're ever explaining something, you never want to say, even though it's so true, like dissolves like dissolves like dissolves like. You want it in your head, but you don't actually want to use it as part of your explanation, okay? What does it mean? Well, what does the AP want you to say? They want you to say, if it has similar intermolecular forces, then it's going to dissolve in something that's similar to it. So, and you want to be even more specific. If it's polar or ionic, if the solute is polar or ionic, then that will dissolve in a solvent that is polar, but it will not dissolve in something that's nonpolar, okay? So you want to check to see what the solvent is. Nonpolar molecules, on the other hand, will dissolve in nonpolar solvents. Pretty easy, okay? So we know gasoline floats on water because gasoline is actually nonpolar, whereas water is very polar, okay? So question 7 says, decide whether hexane or methanol is the more appropriate solvent for grease, and then potassium iodide, okay? So go ahead, and if you want to pause and take a guess here, let's see what you decided. Okay, so for grease, we've got C20H42, which means that it's going to have the 20 times 2, which is 40 H's, plus the 2 at the end. That should be nonpolar. And if it's nonpolar, then which one of these is actually nonpolar? Did you guess hexane? If you guessed hexane, you are right. Okay, so hexane C6H14 is actually going to be our more nonpolar solvent. Potassium iodide, this is ionic. And And so if it's ionic, I want the solvent that's going to be more polar, and so water would be my best choice, right? But in this case, I would rather use the methanol, okay? So if you're trying to decide which one, then that's how you would do that, all right? Solution process. So the solution process it's not just you drop it in and then it separates in water, for example, okay? So it happens in steps. So it's best always if we can watch a video. Let's take a look here.
Sodium chloride crystals are held together by attractive forces between the positively charged sodium and negatively charged chloride ions. When a crystal of sodium chloride is placed into water, the hydrogen ends of polar water molecules attract the negatively charged chloride ions and gradually surround them. Likewise, the oxygen ends of water molecules are attracted to and surround the positively charged sodium ions. The hydrated ions drift away into the solution, allowing new water molecules to surround newly exposed ions. Gradually, the entire crystal dissociates into solution.
So it actually is 3 steps, okay? So the first thing that needs to happen is the solute has to separate ion from ion or molecule from molecule. And in order for that solute, in that example, it was salt, energy needs to be absorbed. So always, remember when we were talking about things like Coulomb's law, for example, and trying to separate these ionic substances from each other, these crystals, it's going to require energy, okay? The second step is the solvent ends up separating from each other. Okay, so like the water molecules are actually separating from each other because they're making room for the solute particles. And the third step is what we call solvation. And so that's when the solvent actually surrounds the solute and that releases energy. Why? Because there's an attraction. Okay, so if it's polar with an ionic substance or polar with another polar or nonpolar with nonpolar, there's a particular affinity or an attraction, and so there's a release of energy when that ends up happening, okay? So both steps 1 and 2 actually require energy. Step 3 is the one that releases energy. So this is why when we did the hot pack and the cold pack, and all we simply did was dissolve something in a bag of water, one was hot, exothermic. The other one was cold, endothermic, because it depends on the entire solvation process. You have to look at all 3 steps and calculate the energy for all 3 and then figure out if your net is positive or your net is negative. And that's how we could tell mathematically if it's going to be exothermic or endothermic, okay? Just kind of a little bit of a side note here. 2 liquids, nonpolar, can create a solution because of randomness, okay? So similar to when we were even talking about the fact that we have like LD forces, for example. So it's just randomness that happens, and then they can create a solution that way. In general, spontaneous reactions occur, and to be spontaneous just simply means we don't have to add outside energy for it to happen. And when this happens, so we just say that the energy actually will decrease, so the amount of energy necessary actually decreases, or we'll say that randomness will actually increase. Okay, and so the randomness or the amount of disorder, for example, must be increasing. All right, let's take a look at a couple more things here. So we've been talking about solubility. What we already said was, we said that this could be grams or moles, but of the solute. And then we said that it would be liters of solvents. Now, a lot of times people will mix up solubility with density, okay? And yes, we know that density is mass per unit volume. So both of these are mass per unit volume. So how are they different from each other, okay? Well, density is, if I said I gave you a cube of gold, for example, and I want to know the density of it, it's the mass of what? Well, there's no solute. It's the mass total, so the total mass of the substance, so the grams total. And then what you do is you take the whole piece of gold and you weigh it, okay? And that's how you get the mass of it. Then you figure out what the volume is of that, and so we just simply divide it by the volume total. And so actually we can even put that it would be like liters or milliliters, whatever you want, but some unit of volume. So we can even do milliliters total. And again, they can use you can use centimeters cubed, for example. Okay, so you can use something cubed that would also be a unit of volume. Okay, So just as a recap here, we said that for the solute particles to separate from each other, that always requires energy. It's positive and endothermic. The solvent particles have to separate. They don't want to really separate, so that's also positive. But when the solvent surrounds the solute, it's negative and exothermic because there's an attraction, okay? So there's a little bit of a release of energy. So if you calculate and your positives are greater than your negative, then that means that the solution, that it'll be endothermic and your sign should be negative. If your positives are less than your negative, then your negative is greater, then it should be an exothermic, I'm sorry, this was endothermic, positive, then this should be exothermic and negative, okay? And so that's how you could tell if you were given those three parts, okay? Another example here, this is just talking about salt dissolving in water. We can actually see that the values here are very close. We've got 786 and a negative 783 for it to come together. And so we would just say that when we add the two together, we actually get a positive 3 kilojoules per mole, which means that it is an endothermic process, okay? And so if you were to put a thermometer inside of there, then what we should see is that it should feel colder. Not by much, but still feel colder, okay? And so the dissolving process requires only a small amount of energy, and processes run in the direction that leads toward having a greater disorder. So in any situation, we always want disorder to be increasing, okay? Now, pressure has little effect on solubilities of solids and liquids, but it is significant in gases. So the solubility of a gas in a liquid, what does it depend on? Well, you know, it actually depends on, a lot of times people don't even know this. If we think about like being underwater, for example, okay, or scuba diving, or if you think about water quality, for example, okay, well, the solubility of a gas, if you increase the pressure on it, then it's actually greater when you increase the pressure. So think of a can of pop, for example, or a bottle of some type of like soda, something that's carbonated, okay? We know when we open up the top and we release the pressure, those gases come out, but you couldn't see the gases before. You're like, wait, there was gas inside of there? It was gaseous, it was CO2, right? Carbon dioxide gas. And so if you have a greater pressure, you can actually get those molecules to dissolve more. So I always want you to think about pop cans or bottles of pop, something like that. That's typically very helpful when you're thinking about solubility of a gas when you increase pressure. So increased pressure increases the probability of a gas particle striking the surface and thus getting trapped. There's something called Henry's Law, and they have gotten rid of it on the AP, but as far as just conceptually making sure that we have that, have this down, what Henry's Law basically states, it's pretty simple, but there's a constant. So this is the solubility of the gas in the solution phase. And this is what the partial pressure is of the gas over the solution, okay? And so what his laws just states is that the amount of gas dissolved in a solution is simply directly related or proportional to the pressure of gas. So how much gas you have dissolved is proportional to the pressure of gas. In other words, you increase your pressure, you increase your amount of gas dissolved. Okay, so we're going to say directly related or directly proportional to the pressure of the gas. Okay, and last thing is, what about temperature? Okay, now this is weird too. Okay, we know that typically, like if you want to make Jell-O, then you want the water to be hot. If you want your coffee creamer to dissolve, if you got like the solid coffee creamer to dissolve inside of your coffee, you want your coffee to be hot. If it's cold, if you've ever tried it, it kind of gives you this like film on top and it doesn't like mix in well, okay? So for the most part, when you have specifically like ionic solid, well, different solids, they usually will dissolve better in hot water. I will tell you that eggs, for example, it works opposite. So if you're ever trying to get eggs out of like a pan or something and you want to let it sit, it's because cold water works better. Actually, it alters the proteins a little bit, okay? So how does temperature work when we're talking about gases? This is weird. As you increase the temperature, so as you increase the temperature, this is for gases, okay, this is only for gases, your solubility actually decreases. You decrease the solubility of the gas, okay? The solubility decreases. Now, anybody that has taken AP or is taking AP Environmental Science, you might know this, or maybe in bio, you may have spoken about water quality a little bit. The amount is greater in colder water temperatures, the amount of dissolved oxygen. And so remember, if you have cooler water and you have more dissolved oxygen, well, that's better for fish and for anything that's going to be living. So you should have more life if the water is actually colder, okay? For solids, though, if they dissolve endothermically, solubility usually increases as temperature increases, but it could decrease. Like I said, there are certain substances like sodium sulfate actually works opposite, so different things go in different directions, okay? And the last thing that we're going to talk about here is Rayote's law. And Rayote's law basically just is regarding lowering vapor pressure of a solvent by a non-volatile solute, okay? This is great. It's kind of like a little bit of an intro into colligative properties here. What does it mean to be volatile? Well, if you have a volatile substance, it's simply something that evaporates readily or it vaporizes quickly, okay? So if you think about something like alcohol, for example, like acetone, where we left it sitting and then it just evaporates really, really fast, that's what we would call a volatile liquid, okay? So this is a substance that vaporizes readily. That's how it's usually defined. Okay, so we've got one more equation here to look at. Also been removed from the AP, but good to kind of look at anyway. And so what we see is we've got the vapor pressure of the solution. So this is the vapor pressure of the solution. Okay, this is chi, which is our mole fraction. So, actually, we can write it over here. So, vapor pressure of the solution. Then we have chi, which we know is our mole fraction. And so this is moles of X, but this is specifically of the solvent. Okay, so it does say it needs to be of the solvent. Moles of the solvent divided by total moles is your chi. And then we've got the P, and it's got that little zero. What that means is it's the standard vapor pressure of just the solvents, okay? So this is the standard, under like standard states, standard conditions, vapor pressure of only the solvent, okay? Only the solvent by itself. So this is of the solution when you have them both together, and this is of the solvent, okay? Well, the cool thing is that it doesn't really change by much, okay? And so that's why they got rid of this equation from the AP, but again, they want you to understand it conceptually. So let me show you mathematically what this looks like, okay? So we've got this problem here, and it says to calculate what the expected vapor pressure is, which means the pressure of the gas above the liquid, okay? And it says it's at 25 degrees Celsius, and they take a solution, and all it has is they're going to add sugar, 158 grams of table sugar, sucrose, right to this 643.5 milliliters or centimeters cubed of water. Centimeters cubed and milliliters are the same thing, okay? And it says at 25 degrees Celsius, the density of water is 0.9971 grams per centimeter cubed, and the vapor pressure is 23.76 torr. What does this mean? Okay. This pressure one, this is what the vapor pressure is of water by itself at that particular temperature. Okay, so you would look it up in a chart or you'd be given it. Now, this is a whole bunch of math, but what we were calculating is the vapor pressure of the solution. So what we did here is we needed to figure out what chi was. Okay, we had to figure out what chi was, which means we needed moles of both of them. Okay, and on top of that, they gave us the milliliters of water, and then they gave us the density. So we actually had to switch from milliliters to moles, so to grams and then to moles. And so I did that. I showed both of those calculations. Then I do the calculation for the vapor pressure of the solution. Bottom line is, by adding 158 grams of the sugar, it barely changes. It ends up being 23.46 torr. It was 23.76. What's the main idea? The main idea is this. If you add what is called a non-volatile solute to a solvent, non-volatile means it's not going to vaporize readily, then what happens is it actually will lower your vapor pressure. Why? Because those molecules are actually going to trap the molecules, the water molecules, from escaping. And so what happens is those molecules want to escape and leave, but they can't because they're being trapped by the sugar molecules. And so you don't get as much gas above the liquid, which is what we call the vapor pressure. Okay? And so that's kind of like a little bit of an intro into colligative properties. Hopefully this was helpful to you. Happy day, everybody.